find the specific gravity of the fluid, Sg. In this problem, a cylinder is submerged in a fluid. The cylinder measures 20 centimeters in the radius and 12 centimeters in the height. When submerged, the cylinder exhibits an apparent weight of 200 newtons. When the cylinder is in open air, its weight is 350 newtons. To solve this problem, we'll first write out the sum of the forces in the vertical direction, which equals 0, because the acceleration of the cylinder equals 0. A buoyant force, Fb, acts upward on the cylinder, as well as a normal force experienced by the bottom of the tank, which is equal to the weight of the submerged cylinder. Lastly, the self-weight of the cylinder acts in the downward direction. The buoyant force is a function of the specific gravity. Therefore, we'll solve for the buoyant force, which equals the weight of the cylinder in air minus the weight of the cylinder when submerged. After plugging in these weights, we compute the buoyant force equals 150 newtons. The buoyant force equals rho times g times v cylinder. In this equation, v cylinder represents the volume of the cylinder, which is a function of the radius and height of the cylinder. After plugging in these dimensions, the volume of the cylinder equals 15,080 centimeters cubed. If we convert the units to meters cubed, the volume of the cylinder equals 0.01508 meters cubed. The gravitational acceleration constant, g, equals 9.81 meters per second squared. And the variable rho, the density of the fluid, equals the specific gravity of the fluid times the density of water, where the density of water equals 999 kilograms per meter cubed. After making these substitutions, our equation for the buoyant force reduces to one equation and one unknown variable. And that unknown variable is the specific gravity of the fluid, which equals 1.015. When reviewing the possible solutions, the answer is C.